Well, hello everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we're going to be continuing our discussion on acids and bases. This is Volume 4. That's right, wouldn't you know it, we have already done 3 episodes on acids and bases. And if you are interested at all in viewing those 3 episodes, there's going to be a link in the description of this video called Acids and Bases live streams. It's a playlist. You can view that playlist and bring yourself up to speed, because if you're watching some of this content and you are unfamiliar with it, it sounds a little foreign to you, all of the prior knowledge that is required to understand the content of this live stream is covered in the previous Acids and Bases live streams. Again, it's a playlist, Acids and Bases live streams, if you want to watch that. So, all right, let's get right into the content, shall we? So here we go. This is Acids and Bases Volume 4. So, we're going to go ahead and do a quick review from the last live stream, Volume 3. So in the last live stream, we talked about 3 very, very important properties of aqueous solutions: pH, pOH, and pKa. Now, pH is probably the one with which most of you are familiar. We understand that it specifies the acidity of an aqueous solution. And we introduced the formula for pH last week, wherein pH is equal to the negative logarithm of the H3O+, that's the hydronium ion concentration. And so since we have a logarithm in this formula, last week I saw that as sort of a teachable moment to kind of review our understanding of logarithms. So just briefly, if I take the logarithms of something, what I'm trying to figure out is the number that I have to raise 10 to achieve that x, whatever I'm taking the logarithm of. So here's how it would work, right? We'd have, let's say, log of 10 equals 1. Why? Because 10 to the first power is equal to 10. If I want to take the log of 100, that would be 2 for the same reason. 10 squared, 10 to the second power is equal to 100. Log of 1000 equals 3. If I have the log of 0.01, that's equal to minus 2, because 10 to the minus 2 is equal to 0.01. So logarithms are very, very important that we wrap our heads around them and that we understand them. Otherwise, we won't really understand anything about pH. And I don't want that for any of you guys. So, all right, so we reviewed logarithms, and I like this little graphic representation here. So this is just a graphic representation of the pH scale ranging from 0 to 14, and the hydronium ion concentration values that go along with each of these pH values. And here we can start to understand how valuable and useful pH is, because here we have a very, very wide range of hydronium ion concentrations, all the way down here at 10 to the 0 power, or 1 molar hydronium ion, all the way over here to 10 to the minus 14 molar, which is a very, very small value, a very, very small value. So whenever you have a wide range of data, using a logarithmic scale helps. Excuse me. Using a logarithmic scale helps when you have such a wide range in a data set, because it makes the numbers much, much more manageable. We've specified this range from 10 to the minus 14 all the way to 1, using a very, very compact series of numbers ranging from 0 to 14. Yes, it is entirely possible for pH to be less than 0. It can be negative. That just means that your hydronium ion concentration is greater than 1 molar. And it's also entirely possible for your pH to be higher than 14. This is just the sort of the most common range where most chemists can apply their actual problems to. So, okay. So, and notice also that the lower the pH, the more acidic the solution, right? So if I have a pH of 0, that means I have an H3O plus concentration of 1 molar. If I have a pH of 6, and it's 10 to the minus 6 molar. So that's very, very important. The lower the pH, the more acidic the solution, the greater the hydronium ion concentration, right? And notice also that if we're looking at, let's say if we go from pH 7 to pH 4, we want to know how many times greater the hydronium ion concentration is. Well, it would be 10 to the 1 to 3 times, right? I have to jump 3 pH units to get from 7 to 4. So that means that my hydronium ion concentration is going to increase by 10 to the third, or 1,000. That's how a logarithmic scale works. I already got a couple of messages in the chat. One from David Cherelis says, looking forward to studying for the MCAT, so I'm looking forward to the stream. Thank you, David, and good luck on your MCAT, sir. Got one from Evelyn Kadawa, says, thank you. You're very welcome. Another one from Gary Santee says, nice. Thank you. I appreciate that. So that's just the graphic representation of the pH scale. Hopefully it helps us get our heads around how a logarithmic scale works. So we're going to move on with this review of last week's material. Then we talked about POH, which is pretty straightforward. It's basically the same formula for pH, only instead of specifying in terms of hydronium concentration, we're specifying it in terms of hydroxide ion OH minus concentration. And from there, knowing the formulas for pH and POH, we were able to derive a mathematical relationship between pH and POH, which is very, very useful. So this next slide here is basically just a little derivation for a formula that's very useful. So we already know, and this is something that we discussed in previous streams, that the product of the hydronium and hydroxide concentrations is 1.0 times 10 to the minus 14. And that's assuming we have 25 degrees Celsius, which is the most commonly reported temperature in chemistry textbooks, at least that I know of, right? So if we can manipulate this equation a little bit. So let's say we take the logarithm of both sides. Now we have the logarithm of this product here, H3O plus and OH minus, on the left-hand side of the equation. Then we have log of 10 to the minus 14 over here on the right. Well, log of 10 to the minus 14 is simply minus 14. So that reduces down pretty easily. And then we can use the properties of logarithms to split this logarithm up. If you have the logarithm of a product of two values, then that is equivalent to the sum of the logarithms for each of those values. So we have this equation, log of H3O plus log of OH minus is equal to minus 14. And then multiplying that whole equation by -1 gives this equation down here, where we have the negative log of H3O plus minus the log of OH minus is equal to 14. Negative log of H3O plus, that is the exact expression for pH. Negative log of OH minus, that's the exact expression for POH. And so this equation finally reduces down to this one here in green, which is pH plus POH is equal to 14. And the reason why this is such a useful equation is, say we know pH, but we want to know POH. Well, that's pretty easy. We want to know POH, but we do know pH. All we have to do is subtract the known pH from 14, and that gives us our POH, and vice versa. And again, this is all assuming that we're at 25 degrees Celsius. I just have to make sure I put that caveat in there so I don't confuse anybody. So that was basically it, the relationship between pH and POH. Oh, jumped a slide by mistake. Then we switched gears and we talked about something called pKa. Now we know that Ka, right? Ka is the equilibrium constant associated with a weak acid reacting with water. It specifies the degree to which the reaction proceeds in one direction or another. And we can use Ka values and also pKa values to compare the strength of weak acids. So just going through this briefly, we have Ka, whoops, there we go. Trying to move myself out of the way here. So if we have a reaction of a weak acid reacting with water, that's given by this equation up here, where we have hydronium ion and the conjugate base of the acid, and the reactants and products are separated by those equilibrium arrows, which indicate an incomplete or partial ionization, unlike a strong acid. And so Ka is simply the product of the concentration of the products divided by the product of the concentrations of the reactants. Water, H2O, of course, is omitted because pure solids and liquids are always omitted from equilibrium constant expressions. And pKa is simply just the negative log of Ka. So for the same reasons that the logarithmic scale is a nice compact way of specifying H3O plus concentration, a logarithmic scale is also a nice compact way of representing the acid dissociation constants of weak acids. So it's much easier to compare pKa values than it is to compare Ka values, because Ka values have a wide range. They're all over the place. You have to use scientific notation. Whereas with pKa, it's pretty straightforward. So, and notice also that because it's a negative logarithm, weak acids that have lower pKa values are stronger acids than weak acids that have higher pKa values. So the lower the pKa, the stronger the weak acid. So I hope everybody's following along, because we are going to move right on and get into the content of tonight's video. By the way, if anybody is, if you're having, what am I trying to say here? If you're finding value in this stream, I would appreciate your leaving a thumbs up on this video. I would wholeheartedly appreciate that. And if you're feeling very generous, consider sending a super chat if you want to. No pressure, no pressure. All right, so let's move on. So tonight, we are going to talk about how to find the pH of an acidic solution. So let's say I prepare an aqueous solution of an acid, and I know the concentration of the solution, but I want to know what the pH of that solution is. And there's really two different methods you're going to use depending on whether you have a strong acid or a weak acid. but we're going to put that off to the side for a moment and revisit that later. But for now, I want you to consider a solution of hydrochloric acid, HCl. So let's say I prepare a solution of HCl. I want to know what its pH is. Well, in a solution, in any aqueous acidic solution, there's going to be more than one source of hydronium ion, right? Hydronium ion, that's the conjugate acid of water. That's the acid that is formed when water acts as a base, accepting a proton from an acid which donates it, right? A lot of acid-base jargon wrapped in there. So if any of that sounds confusing, again, you can watch the previous videos in the acids and bases live streams playlist, right? So we have two sources of H3O+. Now, one is very obvious. It's the H3O+ that is generated when the acid HCl reacts with water. But there's also another source of hydronium ion, and that comes from what's called the auto-ionization of water. This is, again, something that we talked about a couple of weeks ago. So that's just water reacting with itself to produce hydronium ion and hydroxide ion. It happens to a very, very, very small degree. So unless you have a very, very, very dilute aqueous acid solution, the auto-ionization of water contributes negligibly, which means that its contribution to the H3O+ concentration is so small that it can be ignored. So usually when we perform pH calculations with acidic solutions, we do not consider the auto-ionization of water to be a substantial source of hydronium ion, and so we just ignore it from the calculation. It's very, very, very easy. So again, I hope everybody's following along because we're going to move right on. So like I said just a moment ago, we're going to learn about how to find the pH of a strong acid solution and a weak acid solution. The methods are going to be very, very different depending on whether the acid is strong or weak. If it's a strong acid, the calculation is very, very simple, and I'll walk you through one in just a moment. If it's a weak acid solution, then the calculation of pH is going to be very, very complicated. And to even take a stab at understanding how to find the pH of a weak acid solution, we need to have a rock-solid understanding of chemical equilibrium. Very, very, very important, because we're going to work out some similar problems to the equilibrium problems that we worked out previously, where you have like an equilibrium constant and initial concentration, and you have to figure out what the equilibrium concentrations are. So again, if that's all lost on you, consider viewing my chemical equilibriums live streams playlist, and that will bring you up to speed. All right, so let's say we have a strong acid solution. We want to know what the pH of it is, right? So let's say that we have a 0.005 molar solution of hydrochloric acid. Well, the ionization of that HCl is going to be given by this equation here. HCl plus H2O yields H3O plus and Cl minus. And notice we have a single arrow here. That single arrow indicates a complete ionization, which means all of our reactants have reacted, and all that we're left with is our products. In this case, the hydronium ion and the chloride ion. And so because this complete ionization occurs, the concentration of H3O+ that you end up with is going to be equivalent to the concentration of the strong acid that you started with, right? So if I have a 0.005 molar solution of HCl, that means I have a 0.005 molar solution of H3O+ because it ionizes completely. And so to find the pH, all we have to do is take the negative logarithm of that concentration, 0.005, and we end up with a value of 2.3. So very, very straightforward finding the pH of a strong acid solution. Now, what if we wanted to switch gears a little bit, and let's say we want to find the pH of a weak acid solution. So let's say we have a 0.005 molar solution of acetic acid, HC2H3O2. Well, the reaction is going to be given by this equation, right? Acetic acid reacting with water to produce H3O+ and the acetate ion, the conjugate base of the acetic acid. But we have these equilibrium arrows here, which indicate a partial ionization, right? So if the weak acid ionizes partially, we have some H3O+ in here, but we don't have as much H3O+ as the initial concentration of acetic acid that we started with, right? Because it doesn't react to completion. So how do we find this guy right here? How do we find H3O+ concentration when we have an incomplete ionization? We need a property, we need a parameter that specifies the degree to which the ionization occurs. In other words, we need an equilibrium constant. We need an acid dissociation constant, or Ka, which we defined in a previous live stream. And furthermore, we have to understand equilibrium because we're going to be invoking an equilibrium type problem where we are given an initial concentration and an equilibrium constant, and we must find the equilibrium constants in order to find equilibrium concentrations in order to find pH. So I know that was a mouthful, and I'm going to walk you through an example of how this works. So right here, let's say, let me move myself just a little bit. So let's say I have that example, right, where I have a 0.005 molar solution of acetic acid. And let's say I look the Ka value, the equilibrium constant value, up in my textbook, and I find it to be 1.75 times 10 to the minus 5 at 25 degrees Celsius. So that, knowing the equilibrium constant is very, very important. You cannot solve these types of problems without it. So with an equilibrium problem, generally we'll set it up like this, where we have the reaction equation shown at the top here, and then we have what's called this ICE table. I is initial, C is change, E is equilibrium, and then we'll populate these values and then see if we can derive a quadratic equation for the equilibrium concentration of H3O plus, and then solve it. So let's go ahead and walk through this problem. Let me just going to take you to the whiteboard, and then let me grab the problem and paste it so that we can start solving this. Anybody have any questions so far? I would love to hear your thoughts, questions, concerns, any feedback that you are willing to throw my way. Okay, so I'm going to place that up there, and let me know if that's too small. I don't know if that's too small. I know a lot of people are probably watching on their mobile devices, so I can always make it bigger, but there's going to be a lot of scribbling in this, so I want to make sure I leave myself a lot of room. So, okay, so we need to fill out this ICE table. So initial, change, equilibrium. Starting with the initial concentrations. Well, the problem tells us that the initial concentration of acetic acid is 0.005 molar. I'm just going to omit that symbol there just to give myself more room. So 0.005, that's what the initial concentration of acetic acid is, right? Now, initially, there is some hydronium ion in there, right, as a result of autoionization of water. But again, the contribution from water reacting with itself is so small that we're going to just assume that it doesn't exist at all, which is a pretty decent approximation because it's so small. So we can consider the initial concentrations of both of our products to be 0. Okay, now for the change. Well, we know that the concentration of acetic acid is going to reduce. It's going to get smaller by some value that we'll call x. So the change is going to be minus x in the case of the acetic acid, and in the case of our products, H3O plus and acetate ion, we're going to have plus x, right? The concentrations of these guys are going to increase by the same amount that the concentration of acetic acid decreased by. And if you're wondering why I haven't done anything with water, that's because water, its concentration does not change. It's a pure liquid, so we don't have to worry about it in this equilibrium type problem. Okay, so now is the equilibrium row of this table. And so the equilibrium concentration of acetic acid, that's going to be 0.005 minus x. And then hydronium and acetate ion, those are simply going to be x for each of them, right? So now we have the equilibrium concentrations expressed in terms of x, but we have to figure out how to solve for x, how to solve for the hydronium concentration. Well, we know that Ka, right, is equal to the concentrations of the products. In this case, that's concentration of H3O plus, concentration of C2H3O2 minus products over the reactant. In this case, that's HC2H3O2. So that is the expression for Ka, right? That's the expression for Ka. So if we, and we also know that its numerical value is equal to 1.75 times 10 to the minus 5. So 1.75 times 10 to the minus 5 is equal to this whole mess up here. And so if we simply take the values that we have expressed in terms of x and substitute them where they belong in the equilibrium constant expression, then we can set up a quadratic equation. So H3O plus, that is x. Acetate ion, that's also x at equilibrium, right? Another message from Kevin says, hi, sir. Hello, right back at you, Kevin. Thank you for joining the stream. And then the concentration of acetate ion, that is 0.005 minus X, right? So now we have this equation over here, and I'm going to just lasso this and move it so that we can sort of isolate it from, whoops. I practiced doing this earlier, but it doesn't ever go on stream like I practice it. Trying to take this whole equation right here and move it. Oh dear. Microsoft whiteboard. Come on. If I can't do this, I'll just... There we go. Okay, so I'll just move it to the bottom right here. Thanks, guys, for bearing with me in my technical difficulties. Appreciate it. Okay, so let's see if we can clean this equation up a little bit and see if we can solve it. Well, x times x, that is simply going to be x squared, right? So I'll just rewrite that as x squared, right? And then 0.005 minus x, I'm going to do something that we talked about when we were discussing chemical equilibrium, and I'm going to cross out this x. I'm going to assume that this value of x is very, very, very small compared to the number that we're subtracting it from, in this case 0.005. That's the x is small approximation. If you understand equilibrium, then you are already familiar with this. So we can go back and check to see if the approximation is valid, but for now I'm going to make this approximation, and we'll see whether it's valid or not when we solve the problem. So I'm going to ignore that, and so I have this equation right here where I have x squared over 0.005 is equal to 1.75 times 10 to the minus 5. If I simply multiply both sides of the equation by 0. Whoops, I'm off the screen there. My webcam is in the way. By 0.005, right? If I multiply both sides of the equation by that, that will get rid of the denominator on the right hand here. So I end up with this equation, which is x squared is equal to this mess here, the product of 0.005 and 1.75 times 10 to the minus 5. And then to get rid of that square over there, that 2 power, I'm going to take the square root of both sides of the equation. That's going to get rid of the squared over there. And so I'm left with x is equal to the square root of the product of 0.005 and 1.75 times 10 to the minus 5. So what I like to do is I like to algebraically solve these equations in terms of like symbols, and then I'll type this whole expression into my calculator. I'm using, by the way, if you're interested, I'm using this type of calculator here. This is the TI 30X2S. It's pretty old, but it has definitely withstood the test of time. As I always say, I know I sound like a broken record, but please be familiar with your calculator. Make sure that you are using your calculator and you're telling your calculator to do what you want it to do. And I just realized my whole thing is off the page there, so I'm going to move it once again. So x is equal to square root of the product of these two numbers, right? So I'm stalling while somebody enters this into their calculator. I hope at least one person watching this is following along. Doesn't look like anybody's typed it in yet. Lucky for me, I've already solved this problem ahead of time, so I can solve this one. So let's see. What I got was x is equal to, and this is an opportunity for you guys to correct me if I'm wrong. Highly encourage that as well. X is equal to 2.9 times 10 to the minus 4. So that's what x is, and that's also what the hydronium ion concentration is at equilibrium according to our ICE table, right? So if the hydronium ion concentration is equal to 2.9 times 10 to the minus 4, then that means that the pH is simply going to be the negative logarithm of this 2.9 times 10 to the 4. So I'm just going to see if I can do something fancy here. I'm going to copy this, paste it. Oh, I couldn't move it though. Okay, I'll just write it in again. I'm trying to be fancy here, and it always bites me in the ass every single time. 2.9 times 10 to the minus 4. So there it is. Negative log of 2.9 times 10 to the minus 4. What is that number? What is the pH of this weak acid solution? Nobody's answering. Oh no, you guys are breaking my heart. I really hope that one day I can get to the viewership level where people are going to like just answer. I'll just have like my chat just filled up. Oh, I look forward to that day. Should it actually come? I really hope it does. Anyway, so the value that I got, and I'll write this in Green is 2.156. 2.156. So just to wrap up how we solve this problem, right? We have our Ka, we have our initial acid concentration, we set up our ice table, right? We arrive eventually at the equilibrium concentrations expressed in terms of the variable x. We substitute those values in terms of x into the concentrations located in the expression for the acid dissociation constant of the weak acid. That becomes a quadratic equation in which we solve for x. We use the x is small approximation, and that got us the value of x located up here. And then that was the hydronium ion concentration, so we took the negative log of it, and that gives us pH. So if we wanted to, like I said before, we can check to see if the x is small approximation is valid, and what that would entail. Let me see if I can delete a lot of this stuff since we've already used it. I'm going to delete all of that just to give myself some more room, right? Oh dear, that's not deleting. Okay, there it is. It's gone. All right. So Kevin says, because we don't have a calculator like you, sir. Oh, well, they're pretty affordable. They're pretty affordable scientific calculator. I think everybody who studies chemistry should have one. If you don't, then that's going to make doing logarithms pretty difficult. Yeah, if you're going to work with logarithms, definitely recommend getting a scientific calculator. But again, all we have to do is take that value, that 2.9 times 10 to the minus 4. I'll just go ahead and lasso it. And so again, this is just all we're doing right now is just checking to see if the x is small approximation is valid. So all we have to do is take that value and divide it by the number that we subtracted it from, which was 0.005. And if it's smaller than 5% of that value, then we consider the x is small approximation valid. If it's not, then we might have to do a little bit more work. We can either solve the quadratic equation by using the quadratic formula, or we can use the method of successive approximations. And again, if this all sounds foreign to you, I highly recommend studying your chemical equilibrium, and I personally think there's no better place to do it than with my chemical equilibrium live streams playlist. So, okay, we have just gone over how the pH of a strong acid solution and a weak acid solution is calculated. So I think at this point, what we can do is just a couple of practice problems, right? A couple of practice problems just to practice this, to reinforce the concepts that we just learned. And then we can, I don't know. What do you guys think? I want to know what you guys think about this. I think next week, I don't want to jump too far into next week, but I think next week, I just want to do practice problems because we've learned a lot of content and I've only done like a couple of examples or like one example with each concept. And I think it really takes more than that to really understand the content. So if you guys want to see more practice problems on this stuff, please, by all means, let me know because that's kind of where I'm leaning. So, all right. So let's go to another problem real quick. I'm just going to, if you just give me a minute, I'll load it up real quick. Just going to paste this problem into the whiteboard. Okay, so this is the next problem that we're going to solve. So the problem asks us to find the pH of a 6.98 times 10 to the minus 3 solution of hydrobromic acid, that's HBr. So the first question that we should ask ourselves here is HBr a strong acid or a weak acid? Because that's going to determine the method that we use to find its pH. So Kevin says, yes, sir, we want more practice problems. You got it, man. I will do more next week, next Friday. Next Friday, what is that? The 4th? July 4th? Or no, why did I say Friday? Next Sunday, July 4th. Well, it is the 4th of July, so I don't know. Maybe I'll do one, maybe I won't, but I'm leaning towards doing one. All right, so let's go to this problem, right? pH of a 6.98 times 10 to the minus 3 solution of HBr. So we want to know how to find its pH. We need to know whether it's a strong or a weak acid. HBr, as we should know, is a very, very common strong acid. It is a strong acid. So that means, right, that the chemical equation associated with HBr, hydrobromic acid, reacting with water is going to be the following, where we have HBr, that's aqueous, right, plus H2O, that is a liquid, yields H3O plus aqueous, and it looks like I've run out of room, so I'm going to drag this all the way to the left as far as I can. Oh, come on, man. Sometimes I can get this feature to work. Most of the time I can't. Okay, there it goes. Hydronium ion, H3O plus, and Br minus, which is also aqueous, right? And notice that I've used a single arrow in between the reactants and products. This ionizes completely, right? Which means if we have a complete ionization, that the H3O plus concentration concentration of H3O plus is going to be equal to the initial concentration of HBr that we started with, which in this case is 6.98 times 10 to the minus 3 molar, right? And if we want the pH, all we have to do, I'll do this in green just to make it nice and colorful, is to take the negative logarithm of the hydronium ion concentration, which in this case is 6.98 times 10 to the minus 3. So we got some more viewers in here. By the way, everybody who's hopping in the stream recently, thank you for being here. Welcome to the stream. And any comments, questions, concerns you'd like to throw my way, I am happy to receive them. And of course, any super chats that you might want to throw my way, I'd be happy to receive them too. They'd be very welcome. Okay, so I'm just stalling while somebody gives me an answer here. There's like 10 people in here right now. Somebody can calculate this. Negative log of 6.98 times 10 to the minus 3. No takers? I need to start offering like prizes or something. Maybe I'll give you like a little bit of cryptocurrency. Not that I have much, but maybe I'll like give you a little bit of Bitcoin or something if you can answer these questions correctly, just to drive some engagement. So, all right, the value that I got was, where is that value? I got 2.156. So, you know what? I think I actually messed up this problem. Or not this problem, but the previous problem. I think I was reading off the wrong thing. Sometimes, like, I make these cheat sheets ahead of time just so that I can follow along and I don't have that, like, deer in the headlights live stream moment where I get lost. But I think I might have given you the wrong answer to the previous question. But the solution to the problem remains the same. Oh, looks like I got a new subscriber. Cool. Thanks for subscribing if you happen to be here. All right. So it looks like Keystone has typed in 2.156144577. Yes, according to your calculator, that is correct, but notice that I've cut it off at the 2.156. Why did I do that? Well, because when you're taking a logarithm of something, the answer has to have the same number of decimal places as the number of significant figures of the original number that you were taking the logarithm of. Since the original number that we were taking the logarithm of was 6.98 with 3 significant figures, I'm going to have 3 decimal places in my answer. But yes, numerically, you are correct. Thank you for your participation. So, okay, now we're going to move on and we're going to do a slightly harder problem here. So let me delete all this stuff and I'll go grab my second problem here. And this is going to be the last problem of the night because this one's going to be pretty long-winded. And then I think, like I said, next week we'll just do nothing but practice problems. And if you guys have any questions or any problems you'd like to see worked out, feel free to submit them, send them, send me an email. There's a lot of ways to contact me. You can contact me on all my socials, all that kind of stuff too if you're interested. But anyway, okay, so this problem tells us to find the pH of a 2.37 molar solution of hypochlorous acid, that's HClO, and that's at 25 degrees Celsius. And the Ka of HClO is 3.5 times 10 to the minus 8. So we have an initial concentration, we have a Ka, right? And that Ka that's given, that tips us off that we're dealing with a weak acid here, right? Because strong acids don't have Kas. Their Ka is just like infinite, right? It's a complete ionization, right? So we have a Ka, that means we have a weak acid. So we need to do an equilibrium type problem to understand what the hydronium ion concentration is and therefore what the pH is going to be. Kevin says, sir, can I ask questions? Yeah, not only can you ask questions, but I highly encourage it. Yes, ask away, please. So anyway, all right. So what we're going to do is we're going to start by just writing the reaction equation out, and we're going to set up an ice table. So I actually have like a blank template of an ice table that I can use here. So I'm going to copy that over real quick, and I'm going to just paste that in here. Yep, there's my ice table. I'm going to sort of expand that, make it bigger, make it nice and big. I can always reduce the size of it later if I need to. Let's see. I think I'm going to have to make this big if I want to fit the entire reaction equation in there. So, okay, so the reaction equation, right, it is HClO. That's going to be HClO, and that's aqueous, plus water, H2O, which is a liquid, is going to react to form hydronium ion, H3O plus, and that's also aqueous, and ClO minus, which is aqueous, right? So very, very important that we understand how to write these equations. If we don't know how to write the equation, then there's definitely no chance at all of being able to find the pH of it. So Gary says, wouldn't the sig figs be only 3 digits in that case? I don't think so. You have to look up logarithms. Logarithms work a little bit differently from just multiplication and division. So yeah, I think with logarithms, again, I'm happy to be corrected if I'm wrong, but I think when you take the logarithm of something, your answer has to have the same number of decimal places, the same number of digits after the decimal as the number of sig figs in the number that you took the logarithm of. But good question. I will look that up and get back to you for sure. All right, so back to the problem here. We have our reaction equation, and so now we can sort of populate this ice table with the initial values. Initially, it says we have 2.37 molar HClO, so I'm going to fill that in, 2.37. Water we can ignore because its concentration doesn't change, and we can assume that the initial concentrations of hydronium and ClO minus are both 0, right? Because the autoionization of water contributes such a small amount to the hydronium concentration. The change, well, we know that the HClO concentration is going to decrease by a value, we'll call it x, which means that the hydronium and ClO minus concentrations are going to increase by that same value, x. So minus x for HClO plus x for both hydronium and ClO minus. So that means at equilibrium, we have 2.37 minus x for the HClO, and then we simply have x and x for hydronium and ClO minus. So at this point, I think I need to resize this ice table so that I can give myself some more room here, because I know I'm going to need it. How do I resize this stuff? Okay, so let's take that. I'm going to resize that down a little bit. Trying to move this stuff to the side so I can get much room. Let's see. Thank you guys for bearing with me. I really, really appreciate it as I work out the kinks here. All right, well, for some reason I'm having a hard time resizing it. So I think what I can do is I might be able to just move it all up. I can move this up and take this and it up as well, but now it's in front of what I need. That's no good. I need to figure out how to rearrange these things. So let me just undo all of that. Okay, what if I just select all? And then, sorry guys. People are leaving. They're like, dude, I'm not going to wait here for this dude to try to figure this stuff out. I got better things to do. And I can't say that I blame you. So let me figure this out. Can I just resize? I don't know what I'm doing. Okay, well, I'll try to write the quadratic equation with how it is right now. Oh, man, this problem is becoming a dumpster fire just because I don't know how to use my software properly. Okay. All right. So I'll start over here. So we know that Ka, right, which is equal to concentration of products, H3O plus and ClO minus, over concentration of reactants, that's HClO. We know that that value is equal to 3.5 times 10 to the minus 8. That's given by the problem, right? And we know that that 3.5 times 10 to the minus 8, if we just substitute these expressions in terms of x into our acid dissociation constant expression, what we end up with is, and I'll go through this pretty quickly. If anybody thinks that I'm going too fast or if I lose you, please let me know. We can figure that out. So we have x multiplied by x. That's going to be x squared over this 2.37 minus x, 2.37 minus x. And again, all I've done to arrive at this right-hand side of this equation here is to put the values of the equilibrium concentrations in terms of x into the equilibrium constant expression, right? I'm going to do that same approximation I did before. I'm going to assume that the x value is much, much smaller than the value from which we are subtracting it. So I'm going to ignore that from the equation. And then let me erase some of this stuff just so I have some room here. Let's see. So this is our equation. If I multiply both sides by 2.37, right, then that gets rid of the denominator down here. So I am left with x squared is equal to the product of these two numbers, right? Let's see if I can just give myself a little bit more room, separate these out a little bit so I can put some parentheses here. x squared is equal to the product of 2.37 and 3.5 times 10 to the minus 8. And then simply to get rid of that squared, all we have to do is take the square root of both sides of this equation. And so x is going to be the square root of the product of 2.37 and 3.5 times 10 to the minus 8. So that's going to be x, which is also equal to the hydronium ion concentration. And then at that point, all we have to do is take the negative log of it, and we have pH. So how are we going to do that? Well, again, you're going to have to learn how to use your calculator and put this whole expression in there. And the value that I got for x, I'll do it here in blue. The value that I got was the hydronium ion concentration is equal to 2.8 times 10 to the minus 4. 2.8 times 10 to the minus 4. That is the H3O plus concentration in this case. And it looks like I'm off the screen again, so I'll just drag this whole thing. There we go. And so to get the pH, literally, all we need to do, and I'll just erase this stuff up here, is to take the negative logarithm of 2.8 times 10 to the minus 4, and that'll give us our pH of this weak acid solution. So if anybody has the answer, I'll give you a little bit of time if you're interested, but I don't know. I'm not sure if I should wait for you guys to give me an answer, because I believe strongly that finding the answers is just as important, if not more so, than knowing them. So I'll just go ahead and write it in just for the sake of completion. I got a pH value of 3.55. Okay? So just to walk through the problem again, right? We wrote out the chemical equation. We set up our ice table. We filled the ice table. We used the values of the equilibrium concentrations that we got from the ice, from the ice table to set up a quadratic equation. And then we solved for our variable, which we called x. We used that approximation, of course. That got us the hydronium concentration. We took the negative log of it to get the pH. So there's a lot of steps in solving problems like these. So, of course, practicing them helps you go through them faster and also more confidently. So that's why I think next week we're going to do some practice problems. So I already have one person in the chat earlier said that he would like to see some practice problems. And if anybody else agrees with him, if anybody else would like to see some more acid-base practice problems from the concepts that we've learned so far, let me know. I would love to hear your feedback. In fact, I need your feedback. I need your feedback if I'm going to do even a remotely good job at this chemistry YouTube stuff. So Kevin just typed in the chat, says, if concentration of two weak acids are different, are very less than their relative strength can be compared. Okay, I'm not following that message, man. I'm sorry. I'll have to decipher that at another time when I'm not live. I don't think anybody watching this wants to see me try to figure out what that message is. But if you want to reach out to me directly, you're more than welcome to do so. I'd be happy to get to the bottom of whatever question you might have. So, all right, guys, that is it for the educational portion of the live stream. If you guys want to hang out a little bit after this and just talk about whatever, I'm not going to include it in the recording of the stream, but you're welcome to hang out and talk. I'd love the opportunity to talk to you guys, get to know you guys a little bit better. I think that'd be awesome. And what else? I hope you have had a wonderful weekend, and I hope you are all geared up to have an amazing, great, safe, productive week this week. I will see you next Sunday. That's the 4th of July, big holiday here in the United States. But I'm going to be streaming. So 4th of July, Sunday, 9 p.m. Eastern Time. I would love to see you back here. And thanks for watching. All right. Take care.